welcome to the 18th lecture. In our previous lectures, lecture number 16 and 17, we have been studying power amplifiers, especially the class A power amplifier, which uses all the whole the whole linear range of the output characteristics of a BJT amplifier. Right. In this lecture, we will find the power gain and the efficiency eta of this amplifier that is given here. The power gain and the efficiency eta for this amplifier. This is a cascaded, a multi-stage amplifier. This is the first stage composed of transistor Q1 working as a common emitter amplifier. As a common emitter amplifier with part of RE is bypassed by a bypass capacitor and part of it is not. And this stage is feeding another stage. That stage involves a Darlington pair transistor. This is a Darlington pair, and it is working in common collector configuration, with output is being collected from the emitter, and it is driving a load that is actually a speaker. So this is how it is working. It has two stages, this input stage and the output stage. The output stage involves our Darlington pair. We studied Darlington pair in our last course, EDC. Right, so given this circuit and this input voltage, we have to find two quantities, AP, the power gain, and the eta, the efficiency. And we studied the formulas for both. For AP, the formula is this. For eta, the efficiency, this is the power, AC power that is delivered to the load divided by the DC power that is being supplied by this battery. And the AC power that is being supplied to the load, that we put in numerator to calculate this eta, we put its RMS value, because RMS is equivalent to the DC or average value. So both formulas we studied in our earlier lectures. So in this lecture, we're going to find out AP and eta given for this multi-stage amplifier. So let's start. AP is P out over P in, and we studied this formula AV squared R in over RL in lecture number, which lecture? That was lecture number 16. In lecture 16, we derived this formula for AP. So that involves AV, and when we say AV, what is AV for a cascaded amplifier, for a multi-stage amplifier? Of course, AV is the product of this first amplifier times the second. So AV1 times AV2 is AV. So that is our starting point, in fact, right? And that is AV is AV1 times AV2. The first amplifier is a common emitter amplifier with part of RE not bypassed, RE1. So the formula for gain for a common emitter amplifier is RC in parallel with the load resistor RL divided by the small RE, the junction resistance, plus the portion of RE that is not bypassed by the capacitor. That is RE1 in this case. And what is RL for this first amplifier? That's interesting. That's really interesting. What is the input? What is the load resistor for this first amplifier? Of course, that is the input resistance of the second amplifier. And what's that? R3 in parallel with R4, because for AC this is grounded. So this is R3 in parallel with R4, and beta times the resistance that we see here, this RE3 in parallel with RL. This 16 ohm is RL, the load resistor. So RE3 in parallel with RL times beta 3 times beta 2 is the resistance that is available here. And we studied in EDC that the junction resistances RE2 and RE3 are negligibly small when we see the input resistance from here. That we studied in EDC course. that the resistance here is approximately equal to beta 2 times beta 3, the beta for this transistor, the beta for this transistor, times the parallel combination of these two resistors. So that is what we put here. Instead of RL, we put R3 in parallel with RL in parallel with beta 2 times beta 3 times RD3 in parallel with RL. So for that, everything is given. RC is given in the circuit, R3, R4 betas are given, RE3 is given, RL is given. Everything is given except the small RE. RE1 is also given. So to calculate that small RE, but before that, AV2 is 1. AV2 is 1 because it is a common collector amplifier or emitter follower. And we studied in EDC course, the last course, that for a common collector amplifier, which we also called emitter follower, the voltage gain is 1. So that's simple. But in this expression, we have only one unknown, that is RE1, small RE1. And we know that is VT over IE1. This is DCIE. And to find this DCIE, we must know VE1, the voltage drop across the two resistors. This voltage is VE1, VE1. The voltage of emitter terminal with respect to ground. The voltage drop across both these resistors, RE1 and RE2. And if we divide that by this sum, RE1 plus RE2, that gives us IE1. But VE1 is unknown. So to find VE1, we know this is an NPN transistor, and VB1 would be 0.7 higher than VE1. VB1 is 0.7 volts higher than VE1. So if we know VB1, we can compute IE and RE. And VB1 is approximately R2 over R1 plus R2 times VCC. So we put the value of VB1, and we know R2, R1, R2, and VCC, everything is known here. So we can calculate VB1 straightforward. Right, we can calculate straight away. We can calculate VB1 that we plug in here, VE1 here, IE1 here, and then RE1 here. So AV. So now we have computed AV, and that is AV is, it comes out to be minus 15.3 times 1 for AV2. That is 1. So AV for both amplifiers, for both stages, is minus 15.3. So now we are ready to compute AP, because AP is, we have studied AP, this is AV squared RN over RL. So we have computed AV. Rn is R1 in parallel with R2 in parallel with beta times Re plus capital Re1. That is the input resistance that we see here. This is Rn. R1 in parallel with R2 in parallel with beta times this junction capacitance small Re1 plus the portion of Re that is not bypassed. Right. So plugging everything in gives us an Rin equal to 2.9 kilo ohms, and then we are ready to compute AP, the power gain. It comes out to be 42,429. So that completes our first part, AP. We have computed AP. So now let's move to the second part and compute the efficiency eta. We know that eta is, what is eta? Eta is the power that we deliver to the load, the max power that we deliver to the load, and we computed RMS value that we deliver to the load divided by the DC power that we draw from the DC source, VCC, times IC. So first let's calculate PRMS. Across load, input power is Vin squared over Rin. Vn is given to be 250 milli peak. So input power can be computed as Vin squared divided by Rn. Rn is, we have just computed Rn 2.9K. Rn. So V in squared divided by Rn. V in is 250 milli. Right. So converting into RMS, we'll multiply that by 0.707, and it comes out to be P in RMS comes out to be 10.7 microwatt. This is the input power, and P out would of course be power gain times P in, because power gain is P out over P in. So P out is power gain times P in. So the P out RMS is AP times P in RMS. So if you multiply to, the output is almost a half watt, 0.45 watt. Right, so we have computed the thing that we have to put in numerator. And to find eta, we find one more quantity that we need to put in the denominator. And that is the DC power supplied by the source VCC. VDC is VCC times IC, but we know we have several ICs here. If we look at the circuit, there are at least 3 ICs. IC, this IC, this IC, and this IC. So we have 3 ICs, and VCC is supplying 2 more currents, this IP and this IP. So actually VCC is supplying 2 IPs and 3 ICs. But IBs are, of course, they are insignificant. These 2 ICs are also insignificant compared to this mega IC, because that IC is approximately equal to the IE that is used to drive the loudspeaker. So in comparison with this IC, all other 1, 2, 3, 4 currents, all 4 currents are negligible. So we'll concentrate only on this current, the load current, IC of the final stage. That's how to ICQ is 3 is the largest. So I have drawn a part of this circuit again here. This is the current we are looking for. How to find out its value, and if we find out this value IC3 that is approximately equal to IC, we'll put that in here to find PDC. Right, so for that IC3 we have to do a little bit of background work. VB2 is, for this Darlington pair, VB2 would be, of course, the voltage divider. By applying voltage divider theorem, we can find the approximate value of VB2, 15 over 15 plus 5.1 times 15. So VB2 comes out to be 11.2, and we know that the voltage here would be 0.7 smaller than the VB2 voltage. That is VB2 minus 0.7, and the voltage here would be further 0.7 lesser than the voltage that we have here. So VE3 is, this is VE3. VE3 is VB2 minus 1.4, 9.8 volts. So that makes the task a bit easier for us, because dividing VE3 by 16 ohms will give us the current IE3. So if we divide this IC3, which is approximately equal to I3 and which is approximately equal to IC, is VE3 over R3. It comes out to be approximately 0.6 amperes, and that is IC. So PDC is VCC times IC. This is 9 watt. So now we are all set to compute eta, the efficiency. We know P out RMS is half of a watt, 0.45 watt, divided by PDC, it's 9 watts, so eta comes out to be 0.05. It's only, this amplifier is only 5% efficient. Very small efficiency. It's only 5% efficient. Right, that's all for this lecture. In our upcoming lectures, we will continue studying more about power amplifiers. Thank you.